let's make a start. Those of you who've not handed in your homework yet, you can come and do it at the end of the class. Please, everybody remember that there are two names that need to be at the top of your homework, your name and your GSI's name. Both are equally important. You can leave your homework here at the end of the class on the appropriate pile, and if you don't leave it here, then the other place to hand it in is in room 340 McCone Hall, and you have until 5 p.m. That's the time when that mailbox room gets locked. So that's assignment number 1. Second announcement is just again remind you about the field trip. So there are 10 field trip times. You should all have signed up for a field trip time on bSpace by now. They start tomorrow at 9 o'clock in the morning. All of the trips last about 2.5 hours. You meet at the north gate of campus on the hour, not 10 past the hour, on the hour, to leave on the trips. Bring a pen and paper. Part of the trip will be along a creek. Given that it just rained last night, this could be more entertaining than it usually is. So please be ready for that. And then at the end of the trips, we'll describe to you what the field trip report needs to be, and there's information about the field trip report on the website. Okay? Any logistical questions? Hopefully we've covered this. Yes? Sorry, say that again? No, there's no need to put your student ID number. Just put your name. Is that right? I think that's right. Yes, just put your name and your GSI's name. 2 names. Anything else? Yeah? Absolutely. Report's due on the same day. The date is on your syllabus. Any other questions? Don't miss the field trip. You won't get the grade. You won't get the points towards your final grade if you're not on the field trip. So it's very important that you go on one of those field trips. Okay, so in preparation for the field trip, we're going to continue our conversation about faults, and we're going to zoom in, having given you kind of an overview of faults on Tuesday, we're going to zoom in and talk specifically about the Hayward fault today, sort of by way of prepping you for the field trip over the weekend. So again, this is just to give you a sense of where we are relative to the Hayward fault. The Hayward fault runs right along here, goalpost to goalpost pretty much for the stadium. It clips the back of Bowles Hall, and it runs around the back of the Foothill dormitory. We're located right here. This aerial photo was obviously taken when this building was being built a few years ago. So needless to say, we are very close to the Hayward fault, and the Hayward fault represents part of the plate boundary. So the plate boundary between the North American plate and the Pacific plate is taken up by this parallel fault, this splay of faults, the San Andreas fault being all the way over here on the other side of San Francisco, and the Hayward fault being here. Okay? So we're going to talk just specifically about the Hayward fault today. I want to acknowledge these 3 folks. One of my colleagues in the department, Roland Bergman, a former student, Matt Delasio, and a current researcher at the Berkeley Seismo Lab, Ingrid Johansson. They, and other students for that matter, have been working on the Hayward fault, trying to understand the Hayward fault for many years, and much of what I'm going to show you today comes from their research, in fact. Okay, so this is the plate boundary that we are talking about. So the Pacific plate is over here, obviously pretty much the entire Pacific. The North American plate includes all of the US, most of Canada, and most of Mexico. So the plate boundary pretty much runs down the west coast of the North American continent. And in some places, it really is a single strike-slip fault. Okay, in some places, there really is just one fault, the San Andreas fault, which accommodates all of the motion between the Pacific plate and the North American plate. In the Bay Area, so down to the south, it's pretty much one fault, the San Andreas fault. And then just south of the Bay Area, about here, on this map, down here, it splits into multiple fault segments. And so this is the continuation of the San Andreas fault proper, but the Calaveras fault actually goes down to the south and connects with the San Andreas fault. And then here in the South Bay, the Calaveras and the Hayward fault split apart. And the Hayward fault, we think of the Hayward fault as then continuing on in the Rogers Creek fault to the north of San Pablo Bay. So these are the primary faults in the Bay Area, so sort of 1, 2, 3, 4, if you think of it like that, those sort of 4 splays. And so the relative motion between the North American plate and the Pacific plate have to be accommodated by motion on these 4 fault systems through the Bay Area. Okay? And it's important to recognize that the reason the Bay Area exists, the reason that we have what we think of, at least what I think of as being a particularly spectacular environment to live in with the Berkeley Hills and the coastal range and the bay in between, is due to the tectonic motion. It's not a coincidence that so many large cities find themselves directly on fault zones. It's because the kind of environment that's generated in these regions is very conducive in terms of a place to live. And what I mean by that is that you have basins. Of course, most of the land that has been built on is relatively flat land. And what that means is it was a basin, as in it was a big hollow, and then it was filled up by sediment, and so you have this nice flat land surface, which of course is very convenient to build on. In addition to that, obviously we have waterways, so early access to transportation provided by the waterways. The bay, of course, provided a great harbor, which is why San Francisco started right about here. And so there is a direct connection between the reason that we live here, the reason that the San Francisco, Berkeley, Oakland, all of these urban centers are located right here, and the fact that this is a tectonically active process. It's not an unfortunate coincidence. There's a direct connection between those two things. Another place you can go and see exactly this is when you go to Japan. The places where most of the population live are the most hazardous places, and it's for exactly the same reasons. Okay, so that's the overview of the plate boundary. We're, of course, located right about here. This little thing, if you can see it, this little thing is the Berkeley Marina. Okay, so we're located right here, pretty much right on top of the Hayward fault. Okay, so a quick recap back to what we were talking about on Tuesday. So when you look at this image, this is obviously a photograph, an aerial photograph. So where's the fault? You can all wave your arms in an appropriate way. Okay, I don't think I can see anybody here. Well, some people seem to have more control of their fingers than others, but I think pretty much everybody is moving their fingers in a horizontal direction. So yes, the fault indeed is right across here. And of course, hopefully you recognize this. I mean, it says this anyway, but hopefully you recognize that this is in fact Wallace Creek, which is what we were talking about extensively on Tuesday. Yeah, I didn't show you this particular image. We looked at some digital elevation model instead of this image, but this is Wallace Creek, the various creeks all converging, and then it runs into the fault. The channel has been offset, and this is where it then continues. So right now it does a right turn, and then it does a left turn. And so this creek here, originally, when it was originally cut, would have been cut in a straight line, right? Just straight down the topography. The creek cut a deeper channel, and then this motion, the motion of the plate, basically moved it over here. And so what's the relative motion on this fault? Right lateral, that's right. And that means that when you stand here and you look over here, this has moved to the right. And when you stand here and you look over here, this has also moved to the right. Okay, so of course this is the right lateral strike-slip motion that we see all along the San Andreas fault. Okay, so now here's another aerial image of a region slightly closer to home. So where would you put the fault on this map? I see you're getting a finger-pointing idea. Okay, so can somebody describe to me why, when we look at this map, how do you decide where to put the fault? Say again? Yeah? Yeah. Okay, so you're basing it on man-made landmarkers, the Berkeley Stadium right here and the Foothill Dome, and I told you that the fault was right behind it. So fair enough. However, if I hadn't have told you that, if you were to just look at the natural geomorphology, how could you decide where the fault is? Yeah. Okay, so what you're saying is that to the left, there's a lot of houses and structures, and to the right, there's a lot of dark vegetation, and so you can kind of draw a line between those two pieces. So of course, that again is talking about the built environment, but that's fine. Yeah. It's where the mountains begin, that's right. So the reason that this is the built environment is that this is the relatively flat land, and so that's why everybody's built here. And there's fewer buildings over here because of the very steep hills, which you're obviously all very familiar with, okay? So again, the geomorphology here is that we have relatively high, well, mountains is an overstatement, hills, relatively high hills, and then adjacent to that we have relatively flat basin. And of course, you will know that as you walk across, or down to the west across campus, you're walking downhill. And so in fact, the elevation is very low and very flat, close to the bay, and as you get closer and closer to the fault, the slope gradually increases, but then you hit the fault, and there's a very rapid increase in the fault. That's right. So the fault runs right down here, and you can tell that it runs right down here just by looking at the geomorphology. That's the important piece here. So here it is marked on the same elevation model here. Obviously, there's something of a vertical exaggeration going on here, but the fault runs right along the base of the hills, as was just said. And then what I want to point out here is Strawberry Creek. Strawberry Creek, you're probably familiar with, runs down across campus. And so Strawberry Creek is active year-round, in fact, and it runs across campus. But it continues up Strawberry Canyon. And so it's shown in blue here. It comes down here, it goes into a culvert, and it actually goes underground. My pointer's... it goes underground across here, and then continues on down across campus. So does that look familiar? Have we seen this before? Okay, lots of nodding heads. What is this telling us? Right lateral fault, right. It's telling us something about the long-term motion on this fault. Okay? So this creek has been offset by that long-term motion over many, many years. So how would we figure out the rate of motion? Say that again. Get the oldest rock where? From the creek? Which bit of the creek? Above the fault, up here? So if I can paraphrase, you find the oldest rock somewhere and then you divide something. But you have the right idea, okay? So what we want to do is, so that this is the creek, this piece of the creek is fixed, okay? Why is this piece of the creek fixed? It's fixed because it's between these two very steep pieces of topography. This piece of the creek is in a relatively small ditch. So this is the part of the creek that moves. So what's going to happen over time, obviously this section is moving in this direction with respect to this section. So when this creek started to be active, it would have been a straight line. So it would have come down here. So think of this as being fixed. And when this creek started to be active, it would have continued straight down. So the way that we get an estimate of the offset is we look for charcoal deposits for carbon in this creek. We get the oldest sample that we can find, because that's the idea. The oldest sample is when this creek became active. So the oldest sample in this creek tells us when the channel was initially cut. So the oldest sample in here gives us a date when this creek was lined up with this creek. Okay? So we get the oldest sample in here, that gives us the time, and then we measure the offset that this has traveled. We take the total amount of offset and we divide it by the amount of time, and that gives us the rate, the velocity, distance over time that this is moving at. Okay? So here's a map to make it a little more straightforward. So this is a map showing the creek. So again, this is the Strawberry Creek coming down to the stadium. And then there's actually another creek. It's much less, well, in fact, it doesn't have water in it. Most of the, sorry, my pointer has stopped working. Does anybody else have a pointer? If anybody has a pointer, I'll be happy to use it. Otherwise, I'll be waving my arms. Okay? So this is still an active creek, so ignore this one. But these creeks are what are called beheaded channels. Okay? There's no water in them for the most part, and there's no continuation of these creeks up into the hills. Okay? So each of these creeks, what's called Hurst Creek, Mining Circle Creek, and Strawberry Creek, they were all at some point aligned with Strawberry Canyon. Okay? So over time, these creeks just keep moving in this direction. New channels are being cut, and the old channels are abandoned by the stream. Okay? So what we do is we go and we measure the amount of offset between the current, the creek in one side and the continuation of the creek on the other side. And so that's 335 meters. We go and we get the age of this channel. So we cut trenches into this channel. We collect multiple charcoal samples, and we use the oldest date that we get. And the oldest date that we get is 32,000 years. Okay? So it took 32,000 years for this creek to move from here. Okay? This is not a rapid process, obviously. Okay? And so if you divide one by the other, you get that the long-term slip rate, so over the course of this 32,000 years, having moved 335 meters, that the long-term slip rate is about 10 millimeters per year. Okay? Very important number to remember, about 1 centimeter per year. So on average, over a long period of time, the Hayward fault, the deformation across the Hayward fault is about 1 centimeter per year. Okay, I told you last time that the plate tectonic rate between North America and Pacific was 5 centimeters per year. So if the Hayward fault is 1 centimeter per year versus 5 centimeters per year, that means that the Hayward fault is taking 20%, accommodating 20% of the strain on the plate boundary. Right? So the other 4 centimeters are being accommodated by other faults, including the San Andreas fault and the Calaveras fault and the Green Valley fault. Okay, so 1/5 is being accommodated on our Hayward fault. Okay, so that's the long-term rate. And of course, that rate includes, we don't know how many earthquakes, but it includes many earthquakes. Presumably, we didn't get one earthquake and it moved 335 meters. Okay? So it required multiple earthquakes to cause that kind of motion. So we need to start looking back into the history to understand the earthquake history in the region. And unfortunately, we don't have a very good record because we don't have written records from this part of the world for more than about 150 years. Okay? So we have a little more than 150 years. We have approaching 200 years. It wasn't until the were they Spanish missionaries? Yeah, of course they were Spanish missionaries set up on the west coast of North America that we have any written records. So it was only when these missionaries were first set up that we started to get information about earthquakes. And so the last earthquake, and in fact the only historical earthquake, as in one that's been recorded, written down, is the 1868 earthquake on the Hayward Fault. And that ruptured this section of the Hayward Fault. So note that it did not rupture the Berkeley section. I mean, this is our best estimate of the total extent of the rupture. But we do not believe that it ruptured this northern section of the Hayward Fault, only this southern section of the Hayward Fault. Yeah. So the question was, is much of this known when the campus was located here? Anybody know what year UC Berkeley was founded? At least I heard multiple of you say the right answer. I'm impressed, 1868 was, in fact, when the campus was founded. Does anybody know when in 1868? Does anybody know when in 1868 the earthquake occurred? Uh-oh. Okay, so I think it was November. It was in the second half of the year. I'm pretty sure it was November 1868 that the earthquake occurred. Campus was actually founded on this location early in the year, and I don't remember what month it was, but I think it was March or April of 1868. So when they founded campus, they didn't know that there was a fault here. And it wasn't until the 1906 earthquake that we really understood the association between faults and earthquakes. So let's remember that piece. But also, it wasn't that they founded it after there'd just been an earthquake. It turned out that they founded it just before there was an earthquake. Okay? We'll talk about this more actually on the field trip when we go to Founders Rock, which presumably will have an actual date. So we'll be able to see what month it was. Okay, so the last major earthquake and the only historical earthquake on the Hayward Fault was the 1868 earthquake on the southern section of the Hayward Fault. It was actually called the Great San Francisco Earthquake, okay, because at that time there was very little construction, there was very few people living on the east side of the bay. That's why Berkeley was founded over here. There was lots of open land. It was originally an agricultural college, and so there's lots of open land, and that's why Berkeley was founded over here. But of course, San Francisco was well built ever since 1849, and so there was a lot of damage in San Francisco caused by the 1868 earthquake. And this is some damage. There was at downtown Hayward, and so this was damage in downtown Hayward. And so this was called the Great San Francisco Earthquake because it did so much damage in San Francisco. Yeah. Do we know what magnitude it was? We can estimate the magnitudes. In fact, that's written right up here. In fact. So we can estimate that it was a magnitude 7 earthquake, and we estimate that primarily based on the length of the fault that we think ruptured. So this is an estimate. Okay. There were no seismometers recording this earthquake in the Bay Area at that time. Okay, so let's continue doing our little calculations. This is the bit we already did. 335 meters over 32,000 years means a long-term rate of 10 millimeters per year. So the total slip in an earthquake like this, a magnitude 7 earthquake, is about 2 meters approximately. Okay. So if the slip is 2 meters, if we have to move for the Strawberry Creek, we have to move 335 meters. Then the number of earthquakes like 1868 needed is 170. Okay? So we would have to have 170 earthquakes like the 1868 earthquake in order to accommodate that deformation on Strawberry Creek. That's a lot of earthquakes. Okay? So that's an earthquake rate of about 1 per 190 years. Okay? Last earthquake on the southern section was 1868. Okay? But still, we don't know when the last earthquake was on the northern section. Okay? So these are all round numbers. I want you to all understand that. These are not absolute numbers, but these are round numbers. It gives us a sense. So now we know that the periodicity that we would expect significant earthquakes is on the order of 100, 200 years. It's not on the order of every 10 years. Okay? So that's the idea here, to get a sense of how frequently these kinds of events might be going on. Okay, so that's the southern section of the Hayward Fault, rather the southern section of the Hayward Fault had this earthquake. So what about the northern section of the Hayward Fault? And so one of the ways that we get at this information is it's called paleoseismology, reconstructing the history of earthquake activity. And so the way that this is done is by digging trenches across active fault strands. Okay? And so this was a trench that was dug across the Mira Vista Golf Course a number of years ago. A number of years ago. And so what they do is they trench, the fault essentially runs right down the fairway here. So they've dug a trench perpendicular to the fault, and they can actually identify where the fault is, and they look for things like charcoal samples and stuff like this that they can date in the fault plane to try and come up with some assessment of when past earthquakes have occurred. And our best estimate is it's been about 300 years since this section of the Hayward Fault ruptured in an earthquake. Getting nervous yet? Okay, so when we look at the past earthquake history, the 1868 really was the only big event that we know about on the Hayward Fault, so obviously located to the south. Other smaller earthquakes, I guess this shows to magnitude 4s, but there aren't any other big earthquakes to accommodate this motion. So we are building up stress, and so as we build up that stress, we obviously get closer and closer to the earthquake. And so I showed you this on Tuesday, I'm going to repeat it, it's very important. And so the process here is that we're building up this stress as the plates move relative to one another. We build up the stress, it creates this deformation, this sort of S shape, up until the point that the fault can no longer has the strength to withstand the stress that is built up on it. It slips, and that is when we get the earthquake. So the whole idea is that the earthquakes are what is actually relieving this strain. So we can keep going out and we can look for evidence of these faulting processes. I mean, now you understand that one of the challenges we have is we need data over very long time periods, okay? But we obviously still can get data for more recent time intervals. You may think, based on looking at this card, that this is very old information, but this is instantaneous when it comes to geologic processes. And so this is Rose Street in Hayward, and there's an offset curve, you can see right here. And so what does this offset curve show? Can somebody describe it first? And then we'll interpret it. Yeah, description, yeah. Okay, but that's an interpretation. So let's first of all just simply describe it. What do you see? Okay, so the curve is offset. This curve has been offset to the right, okay? And so then the interpretation is that there's a right lateral type of motion. So what you're inferring is that there's some kind of fault that looks sort of something like this, and this is moving to the right relative to this side, so it's right lateral motion. Okay? Of course, we know that this is part of the Hayward Fault, and we know the Hayward Fault is right lateral, so that is what we would expect. But what's really interesting is that people have been back to this particular location and looked at this curve periodically, and this is what they see. So this is a close-up from 1974, from 1993, and then from 2005. Okay? So you can see that this curve is being deformed more and more. So when you walk around the Berkeley Hills, and we will do this on the second field trip, and you see all of the potholes just north of campus, all of the deformation of the curves, it is not entirely because Berkeley is hopeless at fixing and building roads. It's actually because there is continuing, ongoing deformation beneath the surface that is causing this kind of process. Okay? And you can see this up and down the Hayward Fault and where the San Andreas Fault is in urban environments to some extent as well. Okay, so there's been no earthquakes in this time interval. Okay? So there is some other process going on that is responsible for this deformation. So not all of the deformation on the Hayward Fault is being accommodated by earthquakes. That's the key